All right, so we are going to now carry on a little bit more about Greek geometry. I'm going to talk about some of the later work that happened after Euclid. And one very important name is Apollonius. Apollonius of Perga, roughly 200 BC, whose name is associated with conics. Okay, he was the expert on conics or conic sections. Now, most of you will have studied conics in high school. You'll know about ellipses and hyperbolas and parabolas and some basic properties. Apollonius knew far more than you would have learnt in high school. And he would have been shocked at the poverty of the things that you're learning. To say, you've left out all the interesting stuff. Okay? So in the ancient Greek times, first of all, they didn't use coordinates. Okay, so our approach these days is via coordinates with x and y, and a parabola is y equals x squared, and an ellipse is x squared over a squared plus y squared over b squared equals 1, and so on. That's not the way the ancient Greeks thought about conic sections. They thought in terms of combining a circle with a line in the sort of the simplest way to get something higher dimensional. So if we take a point and we take a circle in space and we connect all the points of the circle with the line, then we get a cone. Okay, so it's really a combination of a circle and lines, like an ice cream cone, but it's important to realize that it goes on below as well. And it's slicing the cone that creates the conic sections. So what you do is you take that cone and you take a plane and you slice the cone with a plane and you see what the intersection is. In this case it might be an ellipse, or with a different kind of plane. If the plane was exactly parallel to one of the lines, something like this, then you would get a parabola. And if the plane was at some other inclination like that, then you get two branches, one here and one here, so you get a hyperbola. So there's a hyperbola. The first one was an ellipse. And this sort of special one that's sort of intermediate halfway between an ellipse and the hyperbola case, that's the parabola. So that was where the conic sections came from, and Apollonius and others studied these things and discovered many properties of them. Okay. So these days, of course, we know that an ellipse can be thought of in a number of different ways. Yes, it can come from cutting a cone, but it can also be generated by having two foci, having 2 points F1 and F2, and getting a piece of string of a certain fixed length and tying it down to be attached to the two foci, and then tightening it with a pencil so it's tight. And it's flexible, and then as you move the pencil, you sketch out an ellipse. So in terms of distances, that distance is constant. D1 plus D2 is constant. That defines an ellipse. There's another way of thinking about an ellipse in terms of choosing one of these foci and a certain line out here called the directrix. The points are called focus, or foci. And another definition of a conic, in this case an ellipse, but it works for the other conics too, in terms of the focus and directrix is to say, well, we're going to look at a point, x over here, which has the property that if we compare the distance to the focus to the distance, the perpendicular distance to the line, then that ratio is always a constant number. Okay, so that definition is the ratio of the distance between the focus f1 and the point x to the line and the point x, if you allow me to write that. So that's the distance from the directrix d to the point x, the perpendicular distance. That's the distance from the f1 to x. And that should be some fixed number epsilon. And whether we get an ellipse, so if epsilon is less than 1, then we get an ellipse. And epsilon equals 1, we get a parabola. And epsilon bigger than 1, we get a hyperbola. This number epsilon is called the eccentricity of the conic. So what kind of things did Apollonius prove? Well, he proved many things, and I'm going to just mention one or two rather important things that he mentioned that you may not know about. So let's say we take a conic section, and I'll draw it as an ellipse, but it actually works also for a hyperbola or a parabola. And suppose you take a point x, say outside the ellipse. Then one thing we could do is we could draw tangents from that external point to the ellipse. There are two such tangents, one on that side and one on that side, and they meet the ellipse or the conic in two distinguished points. And those two distinguished points determine a distinguished line. And this line is called the polar of the point x. The polar of x. And I hope you can see that as x approaches the ellipse, then these two tangent points are going to get closer and closer together, and the polar is also going to come closer to where x is. So for example, if we're over here, then the polar would be something like this. And sort of in the limiting case, when the point actually arrives on the ellipse, then we would just be talking about the tangent. Well, then my natural question is, well, what happens if we kept on going? Is there a polar of a point like that? Does that make any sense? Well, it certainly doesn't seem to, because you can't draw tangents from this internal point to the ellipse. But there's another construction of the polar, which is somewhat more flexible. So here's another construction. So what you do is you take your point x and you draw any two lines that cut the conic in 4 points. Any two lines. And then those 4 points, you join their diagonals. There's one, giving us a point of intersection right there. And then there's another diagonal obtained by joining this one and this one. And these guys will meet at some point over there. So we can use the places where these two diagonals of this quadrilateral meet to determine the polar line. So let's see if we could, how that would work for an internal point. Here's an internal point. Let's see what its polar is. We draw any two lines. We get 4 points. What are we supposed to do? We're supposed to connect the other kind of diagonal. So there's one here and one here, okay, meeting some point over here. And then there's this one and this one meeting somewhere over here. And then when you connect those up, you get the polar of x again. Yes?
If x moved on a straight line towards the first ellipse, would all those polars of x be parallel?
No, they would all rotate.
Okay.
So so the question is, what would happen if x moves, say, along this straight line? What would happen to all its poles? Well, so the beautiful thing that Apollonius would have said, that's a very good question. He said, what happens is you need to compute the pole of the line that you're moving on. And it would be, I don't know, let's say, for the sake of argument, out here. And what ends up happening is that as this x moves along this line, all the polar lines of x rotate always through this point. That's a fact of the following theorem, that if x lies on the polar line of y, then y lies on the polar line of x. You can read that? Now you might say, well, wait a minute, you seem to be cheating here, because when you started with this definition, or this second construction of the polar, you said, well, just choose any two lines. And then these 2 points that you created were dependent on the 4 points that you chose. Well, what would happen if I chose a different pair of lines? Surely I would get something different. Suppose I moved these yellow lines. Then this point and this point would move, but remarkably, they would just stay on this line. In other words, the line determined by them would be the same. In other words, the construction does not depend on the 2 yellow lines that you've particularly chosen. Very beautiful stuff that you ought to study in high school. You ought to study in high school. If we go back to this original definition business, we started out with a cone. We sliced the cone via planes. We got conic sections. Over here, we had 2 other definitions. We had a definition in terms of 2 foci. And then we had a third definition in terms of a focus and a directrix. Which is the right definition? How do these definitions connect? That's a lovely question that no one seemed to have answered until the 19th century. In the 19th century, it was understood for the first time how those 3 different definitions connect. And it's such a beautiful construction, I'll show it to you. So here's our cone. Make it a bit bigger. There's our cone. I'm going to slice it with a plane. And let's suppose that we get an ellipse. Okay, so that's, we've cut off, we've taken our ice cream cone and sliced it diagonally with a knife, and then the cross section is some kind of elliptic cross section. Where are the foci? Where is the directrix in this story? So Dandelin, in the 19th century, figured out where the foci are. Here's what you do. You start with a little bubble. You put a little spherical bubble at the bottom of your ice cream cone, and you blow it up gently. Okay, it's sitting in your cone. It's like a little sphere. And you let it grow. So it's growing. So it grows. A minute later, it's this big, and it's moved up. Right? As it grows, it moves up. And eventually, at some point, it just touches the plane for the first time. You've got this plane, it's growing, and at some point, it's going to touch the plane. So there's going to be at some point where you've got this sphere sitting inside here, which touches the plane at some particular point. And that point where it touches is a focus. And where's the other focus? The other focus, we do kind of the opposite. We start off with a very big sphere sitting way up, high up on the cone. And we shrink it. We let the air go out of it. So it's getting smaller and smaller. As it's getting smaller and smaller, it's coming down. Originally, it was quite far above our plane, but eventually it will touch our plane in exactly one point, which is the second focus. And where is the directrix? Remember, there was also a line outside the... Well, if you take that sphere that touches it on the bottom, that sphere touches the cone at an equator. It's sitting touching the cone on an equator. If you look at the plane through that equator, that's like a horizontal plane. That plane intersects the plane of our conic in a line. And that line, where this plane and this plane meet, that's the directrix D. That goes with that focus. And there's another directrix for the other focus, which is obtained by taking this plane through this equator and looking where it intersects the line. That's the second directrix. Okay, there's one more theorem that I have to tell you about, which is very important for history of math. That came a little bit later in the story. It's not to do with conics. It's the theorem of Pappus. So Pappus was around maybe 100 AD. And he discovered this very elementary founding theorem. You have two lines, and you have 3 points on one line, and 3 points on another line, on the other line. And let's call them A1, A2, and A3. And B1, B2, and B3. This is a result only involving a straight edge, no compass or anything sophisticated required. We're going to join A1 and B2 and A2 and B1, and we get a new point. Let's call it C sub, maybe C sub 3. This sort of corresponds to the indices 1 and 2. Let's do the same thing over here with A2 and B3 and A3 and B2. We get a new point over here. Let's call that C sub 1, because it comes from A2 and A3 and B2 and B3. So one more thing we could do, we could join A1 and B3. Okay, well I can do it. A1 and B3 and A3 and B1. And they cross at some other point, C2. And Pappus's theorem is that these 3 points always lie on a line. So if C1 is the intersection of A2, B3 with A3, B2, and C2 is A1, B3, and A3, B1. Where those meet, at C3 is, say, A1, A2, A1, B2, A2, B1. This is my terminology for a line. So this is the line A2, B1. And the meets of these two lines, or their intersection, I just get by putting them together. Then the theorem is that C1, C2, C3 are collinear. This is Pappus's theorem. And this is the first theorem in a subject which eventually, in the late European era, 17th, 18th, 19th century, became a very important subject. It's the first theorem of projective geometry. Projective geometry is like a child's geometry. It's a geometry only with a straight edge. No compass, no measurements. Just what can you say if you have a pencil and a straight edge? Not a ruler, just a straight edge. It turns out you can say a lot. And this is the first theorem, and it also turns out it's probably the most important. And perhaps the most important theorem in this subject. And for me, that's one of the fascinating things about the history of mathematics, that often it's the first or the early theorems in a subject which end up being the crucial ones, the ones that are the basis for a lot of subsequent developments. So we'll talk about more about projective geometry a little bit later, but that's the first theorem for it. All right, next time we're going to have a look at number theory in the ancient Greek times. The Greeks also were interested in number theory, and they proved some very interesting things about numbers. So that's what we're going to do next time, and I'll see you then.